musculature, and you're also preventing hypothermia and the risk for cold injuries such as frostbite or frostnick. Protecting the most important regions of your body when attempting to exercise in cold conditions becomes very important. And as I mentioned before, core temperature is exceedingly important, and more important actually than peripheral temperature. Your body, when vasoconstricting, is actually sacrificing the peripheral temperatures for the core temperatures to maintain that in a nice 37 degrees Celsius range. Looking forward, there's been a ton of technological advancements in smart textiles in the recent years, and primarily they've been focused in on thermal comfort for everyday people. One of the large organizations, the research arm of the U.S. Department of Energy, has been putting a lot of funding into this in hopes of reducing energy costs long-term from air conditioning and heating systems, as well as protecting the environment and reducing carbon footprints. At the University of California, the Gorodetsky Group is a participant in this type of research, and they've been focused on controlling of radiative heat using cephalopods such as octopuses or squids as models. The team is adapting the technique to longer infrared wavelengths that carry heat and implement them into clothing. And while the research hasn't really been published yet, they're partnering with Under Armour, and they're hoping to make some progress and hopefully have technologies developed by the year 2020. Another group that's focused on this thermoregulatory clothing is MIT. So this company called Climaware, and they've been focused on nanotech clothing, which utilizes the Peltier effect. This is where electricity is run between two metals, conductors, generating both a cool surface and a hot surface. By implementing these little patches into clothing, they can concentrate heating and cooling in areas of dense blood vessels, which that blood flow is going back to your core, and as a result, you can maintain peripheral vasodilation, maintain that blood flow, maintain an adequate core temperature. So if you look on their website, Climaware, all their products are currently sold out, which is pretty impressive. Finally, we have beaver-inspired wetsuits. This research is also out of MIT labs, and they're developing wetsuits that mimic the fur of beavers and sea otters. So beavers and sea otters have these pockets of air that's inside of their dense fur, and this trapped air serves the function of an insulator, just as down feathers, fleece, or wool has done in the past. So they're really trying to focus on this technology and implement it into wetsuits. Just a little quote from one of the lead researchers: "We can control the length, spacing, and arrangement of hairs, which allows us to design textures to match certain dye speeds and maximize the wetsuit's dry region." And the main practical application for these right now is wetsuits for surfers, but I think they can be applied to a whole ton of different clothing garments in the future. So we just have a little video for you about the research they're doing. It's pretty cool, so check it out.
Inspired by hairy semi-aquatic mammals such as beavers and sea otters, a group of MIT engineers are fabricating fur-like rubbery pelts to learn how these mammals stay warm and even dry while diving underwater. The group's research was initially motivated by a visit to a company who manufactures wetsuits. The company was interested in developing materials that would keep surfers warm and nimble while they move in and out of the water.
So our first thought was to take inspiration from biological systems, and we started looking at animals that are small and agile but have to survive in Arctic environments and spend part of their time underwater and part of their time on land. One of the interesting things we learned about these marine mammals is for small mammals that can't carry around a lot of blubber but still need to maintain warmth, have a very specialized fur that traps air when they dive underwater.
And so what we're interested in doing is trying to understand what parameters of their fur, how fast they're diving, the properties of the liquid, how do these all come together to inform us how the air gets entrained.
For their experiments, the team fabricates precise fur-like surfaces of various dimensions using molds and a soft casting rubber. They then plunge the surfaces in liquids with varying viscosity and at varying speeds. Then, with video imaging, they're able to measure the amount of air that is trapped in the fur during each dive. What they found was the spacing of individual hairs and the speed at which they were plunged play a large role in determining how much air a surface could trap. Based on these findings, the team developed a simple model to describe this air trapping effect in precise mathematical terms that can be applied to various materials manufacturing processes.
For example, wetsuits are now made of thick neoprene rubber, but what if we used a much more lightweight material, something with a hairy texture, and instead of using rubber, we're using air for insulation, and it could be a lot more lightweight and still effective in water.
Beyond that, I think, textile design is turning into a really interesting field right now. We have a lot of new manufacturing techniques, we have a lot of new materials that enable us to build new fabrics that can have specially tailored thermal properties, that can have specially tailored sensors. I think all of this ties into these ideas about quantified self and sort of the new types of clothing that's going to be available to us in the upcoming years.
So I hope you guys enjoyed our presentation on technological advances in thermoregulatory clothing.
Thanks for watching. Have a good night.